Now we'll see some gate questions related to pipelining. The first question is from gate 2008 IT paper and 40th question. Let us read the question. A non-pipeline single cycle processor operating at 100 megahertz is converted into a synchronous pipelined processor with 5 stages requiring some timings. Okay. So let us focus on this first line. A non-pipelined single cycle processor. That means you can imagine that non-pipelined single cycle processor like this. There is a circuitry. Okay. This is circuitry. Whatever. Now the circuit is working with single cycle. That means within single cycle it is producing the output. Okay. Now it will do all this instruction execution, fetching, decoding, everything. It takes one clock cycle. Understand? Single cycle. So what is the cycle duration? 100 megahertz. So they have given frequency. There is a relation between frequency and clock cycle. So this is the right time to understand what is the difference between clock cycle and frequency. Simple. If you want to find out the clock cycle, the time duration of execution, then simply divide this frequency by, simply you use formula 1 by frequency. What is frequency? Because time equal to in your physics classes, right, in intermediate you have learned, right, time equal to 1 by frequency, correct, time period equal to. Similarly here also this clock cycle's time period equal to 1 by frequency, which is nothing but 1 by 100 megahertz. So this is simple formula. If I simplify it, then hertz is nothing but 1 by 100 megahertz is nothing but 1 by 100. Mega means 10 to the power of 6. Hertz means 1 by second. Okay, 1 by second. So that that entire thing will become seconds. Now it will become 1 by 100 into 10 to the power of 6. It will be 10 to the power of 8. If it goes up, it will become 10 to the power of minus 8 seconds. Then if I convert this to nanoseconds, because see we have some values which are in nanos, then I can say that it is 10 into 10 to the power of minus 9. So that means 10 to the power of 10 nanosecond, isn't it? Finally, in the first non-pipelined single cycle processor, we have a time period, right? That is nothing but 10 nanosecond. Just remember it. 10 nanosecond. Non-pipelined. That is converted to a synchronous pipelined processor with 5 stages. What is the meaning of synchronous? I will tell you. Whenever a pipeline is synchronous, this is a definition of synchronous pipeline. So you will be having a common clock for every stage. That means, example, let's say you have, let's say 3 stages. This stage takes 1 hour. This stage takes 2 hours. Just for easy understanding, I am giving values in hours. So this is taking, let's say, 4 hours. And in synchronous pipelines there will be a buffer between them, just whatever we have discussed in our in our sessions, they are nothing but synchronous pipelines. So what happens is, so this stage will work and it will produce the output, and that will be transferred to this buffer. Now this stage will transfer its data to this buffer, and of course this buffer is unnecessary in that way. Okay, this stage sends the data to buffer and this stage sends the data to buffer, we know that, right? And this stage generally doesn't require buffer. Now what I want to say is, example, let's say this stage takes 2 hours, because after 2 hours only it is producing the result and it is keeping in the buffer. But this fellow is doing things fast, right? Within 1 hour he will produce 2 outputs, and he will replace the previous output. Try to understand. In the first hour he will put the result here. Let me show here, result 1. But he takes 2 hours. Then he is not going to take this result because he is still working, correct? His computation is not done, right? So what he will do? So he will take 2 hours. Meanwhile, this stage again will work and it will do one more result. It will produce another result and the previous data will be replaced. So that is a problem with uneven stages. Whenever there are uneven stages, if you want to have synchronous pipeline, then the best thing is, though it is taking 1 hour, then what we have to do is, we should say that, my dear stage, you have to work only once per clock cycle. So I am telling this stage, my dear stage, you will be allowed to work only once in a clock cycle. Though you are fast, you are capable of doing the things 2 times. But what I do is, because this, your fellow stage is taking 2 hours and there is another stage which is taking 4 hours, then I fix clock cycle in this model to 4 hours, and I say that stage number 1, only within 4 hours you have to respond, all your circuit should be responded only once. Okay, so after 1 hour though you produce, then remaining 3 hours you cannot work. Because, so generally how we can make it, I will tell you. There is a concept called edge triggered circuits. So that if your cycle is like edge triggered, then what happens, when this triggering occurs, so at that time I can say that this entire device will work. Later in this remaining period it won't work, so that it will produce only output once. Understand? That means throughout the clock the circuitry is not working. Understand? Because of that, so somehow you understand like that, that is enough. So within one clock cycle this device or this stage will produce output only once, then remaining 3 hours it will keep quiet. Then in the second clock, again this stage will start working and it will produce the second output. In that way, for every 4 hours only once this buffer will be filled, that's it. So that there will be a synchronous pipeline, so that everyone will work in harmony. Understand? So there will not be any problems. So now if you understand that idea, easily we can solve this problem. Did you remember the first non-serial pipeline took 10 nanosecond, right, to execute one instruction? Remember that point. Now the second one is synchronous pipeline with the uneven stages, right? Let's see the stage delays. One is 2.5 nanosecond, second one 1.5 nanosecond, third one 2 nanosecond, fourth one is 2.5, 2.5, 1.5, 2, 1.5, 2.5, right? And you know that there will be buffers also. The delay of the buffer, latch means here buffer, latch is also known as buffer. So here buffer delay is uniform 0.5, okay, everywhere 0.5, 0.5, 0.5. Here clock delay is 3 nanosecond, right? So that's why I can say that first instruction takes, how many stages we have? 1, 2, 3, 4, 5. So it takes 3 into approximately 5, 15 nanosecond first instruction. But we know that after that, for every 3 nanosecond one instruction will be executed. Now in the long run, so if you see, every instruction is taking only 3 nanosecond here, but here it is taking 10 nanosecond. Then we know the formula for speed up. What is the formula for speed up? Speed up equal to the time taken in the non-pipelined processor, 10 nanosecond, by the time taken to execute instruction in pipeline processor, 3 nanosecond. So it would be 10 by 3, which is nothing but 3.33. Hence option C is the right choice. In that way easily we can solve pipelining questions. Now we'll see one more question which is asked in 2015 paper, set 1, 38th question. Consider a non-pipeline processor with a clock rate of 2.5 gigahertz. Let us stop here. So it is a non-pipeline processor with a clock rate of 2.5 gigahertz. Already I told you. Then what should be the clock period? Clock period is nothing but 1 by this frequency, 2.5 hertz, right? Gigahertz. Remember one thing, giga means 10 to the power of 9. So because of that it will become, so it is 10 to the power of 9, 2.5 into 10 to the power of 9 hertz. Hertz means 1 by second. So it would become 1 by 2.5 into 10 to the power of 9. If it goes up, 10 to the power of minus 9. So 10 to the power of minus 9 and 1 by second is nothing but if it goes up second, right? 10 to the power of minus 9 second by 2.5. So 1 by 2.5 is nothing but 0.4. Just simplify and check it out. 0.4, 1 by 2.5 into 10 power minus 9 second is nanosecond. So what I am doing is I am converting that answer into nanoseconds. Finally, this entire thing is 0.4 nanosecond. Remember it. So the first non-pipelined processor's time cycle, that means cycle period, is 0.4 nanosecond, remember. Second one, and it is given that average cycles per instruction in this processor to execute one instruction, how much time it will take on average? It is 4, right? 4 cycles. But what is cycle time? 0.4 nanosecond. Then can I say that to execute one instruction on average it takes 4 into 0.4 nanosecond, which is nothing but 1.6 nanosecond. Remember that point. Now the remaining information, if you see, such processor is upgraded to a pipeline processor with 5 stages. Fine. But due to internal pipeline delay, you know that because we keep buffers, right? So this is your new idea, pipelining model, where you will be adding some buffers between them and some extra hazards, circuits, everything. Because of that there is a delay. That internal pipeline delay of the, because of that, clock speed is reduced to 2 gigahertz. So it was 1 by 2.5 gigahertz, now it is 2 gigahertz. Now we are in pipeline model. In pipeline model, cycle time is nothing but 1 by 2 gigahertz, correct? Same formula like non-pipeline. So 1 by frequency, it is nothing but 1 by 2 into gigahertz. If it goes up, it will become nanosecond, remember it. So if you still don't have clarity, 1 by 2 into 1 by gigahertz, 1 by giga means 10 to the power of 9, hertz means 1 by second. So 1 by second, if it goes up, it will become second. So let me make it second here. So 1 by 10 power 9 is 10 power minus 9 second. 10 power minus 9 is nano. So from now onwards, whenever you have 1 by gigahertz, I blindly convert 10 nanosecond. So it is 1 by 2 into 1 by gigahertz, which is nanosecond. So which is nothing but 0.5 nanosecond. The clock was 0.4 nanosecond. Sir, because of pipelining, are you getting more time? That means instructions are getting more time? No. Though clock is increased, but we have parallelism. Because of parallelism, you get the benefit. So it takes only 0.5 nanosecond for execution, right? So first instruction takes 0.5, 0.5, 0.5, 0.5 and depends on number of stages. So 5 into 0.5. But in the long run, for every clock cycle, one instruction will be outputted. We know that, right? That's why I can say that each instruction is taking here only one clock cycle in the pipeline model. So each instruction time here only 0.5 nanosecond, right? Don't use this one, sir. Each average cycles per instruction is 4. That is in non-pipeline. In pipeline, so the instruction execution time is only one stage delay. That means one clock cycle. So that's why 0.5 nanosecond. Now come to the problem. What is the maximum speed up you can achieve? What is the time it takes for instruction execution in non-pipeline? 1.6. Formula is very simple. Time in the non-pipeline by time in the pipeline. Time in the non-pipeline is 1.6 by time in the pipeline is 0.5. If you simplify, it will become 3.2. So this is the speed up factor. Okay, in that way easily you can solve. See this example. So which is asked in GATE 1999, question number 13. So there are 5 instructions I1, I2, I3, I4, I5 and their clock cycles are given for each stage. Fetch takes 1 clock cycle, example I1. Decode takes 2 clock cycles and execution 1, write back 1. Second instruction takes 2 clock cycles for decoding, 2 clock cycles for execution. In that way, variable number of clock cycles they are taking. Then the question is, how much time these instructions will take to get executed? That's the question. We will see that. First of all, let us schedule I1. So I1 will be scheduled here, right, for fetching. So instruction 1 will be fetched here and decoded for 2 clock cycles and executed for 1 clock cycle and write back will be for 1 clock cycle. Then later second clock instruction comes. So second instruction should be fetched where? Definitely here, because we have a choice. Now since it takes 2 clock cycles for decoding, we can't allow decoding here because already decoding circuit is busy. Then let us put dummy operation. That means there is no operation here. Then here second instruction will be decoded, again decoded. Then after that execution 2 clock cycles, write back, right? 1, 2, 2, 1. Now after that third instruction comes. So what is my suggestion is, don't fetch third instruction in the third clock cycle. Don't do that. If you do that, what happens? See, in the second clock cycle you fetched second instruction. In the third clock cycle, if you fetch the third instruction, then since still second instruction is not decoded, correct? Now, if you fetch the third instruction in the third clock cycle, that will occupy the buffer of second instruction. Understand? So for that I will explain with example. You have, let us observe the buffers so that you can understand. I am talking about a buffer between instruction fetch and decode. This is, let's say, fetch stage, this is decode stage, there is a buffer between them, right? Okay. Now end of the first clock cycle, what happens, we'll see. End of the first clock cycle, we know the story of pipelining, right? End of the first clock cycle, what happens is, instruction 1 will come to this buffer, so far no problem. At the end of the second clock cycle, since you fetched in the second clock cycle, you fetched instruction 2, then that instruction 2 will come to this buffer. This is fetch decode buffer, right? So that, why we do that? So that in the probably in the next clock cycles, this instruction 2 will be, decoded, correct? Now in the third clock cycle, you are fetching it again at the, so second clock cycle, this is a picture. At the end of the third clock cycle, you are fetching this instruction 3. When you do that, so I3 will be replaced, I2 will be replaced, correct? But so far you did not decode it. If it is already decoded, let's say, if it is already decoded here, there would not be any problem. But now it is problem for us, right? So definitely there is a problem. That's why don't fetch here. When you fetch it, you are unnecessarily replacing the second instruction. You are erasing the second instruction, which is not at all decoded yet, right? So that's why this kind of pipelining understanding is important. That's why so we have to study the things in very depth. That's why we spent a lot of time in understanding the circuitry related to pipelining, right? So here you get the benefit. Otherwise you can't understand this kind of minute details, right? So you will be fetching here unnecessarily. That is wrong. Then what we have to do is, here you are not. So that means this blank says that don't fetch here. Come here, fetch. Now if you fetch here, see I3, everything is now same. I3 takes 2 fetches, right? Here 2 clock cycles to fetch. Then 1 clock cycle to decode. Yes, we can decode here. Then after that, execution takes 3 units, but here we can't do because already execution stage is busy. Then we will be doing execution here, here, here. Okay, 3 executions followed by 2 write backs, right, right. Now comes fourth instruction. So fetching 1 unit. So we can't fetch here, we can't fetch here, we can fetch here, right? So after that, decoding 3 units. We can decode here, right? So we decode here. Then if you decode, what happens? Here you are going to execute this one, then you will be unnecessarily replacing this place. That's why don't do that. Same thing, correct? So before here, between decoding execution, don't decode your thing, so that this decoding information will be unnecessarily cancelled, correct? That's why don't do that. Here you do, right? By that time already, so this decoding information is used by this execution. That's why here decoding. Then focus on fourth instruction. Fourth instruction requires 3 decoding stages, D, D, D. Then after that 2 executions, then followed by 1 write back. Now comes fifth instruction. So fetching. So here definitely, can you fetch here? Don't fetch, because this gap says that don't fetch. If you fetch unnecessarily, between it is like fourth instruction is fetching here, decoding here. In between, if you write fetch, then this fetch will replace the buffer of this fetch, correct? Like this. So that's why don't do that. So you fetch here. By that time, previous instruction is getting decoded, no problem. Then after that, your decoding requires 2 units. Then don't do here, don't do here. Do decoding here, correct? So after that, one more decoding, because 2 clock cycles. Then after that, execution 1, write back 2. So this is the final idea. So 2 things you remember: when a stage is busy, we can't use it. Second thing, when an example here, so second issue is this one. when some instruction is getting fetched and decoded, in between don't try to fetch. That means between any two operations of one instruction you should not go in between, and you should not change this buffer. That is what I explained clearly in the first example itself, right? So you focus on that, and we will be repeating the same thing throughout the example. Okay, so finally if you count the number of clock cycles, 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15, so 15 clock cycles are required. In that way you can answer this question. See this example which is asked in GATE 2005 paper IT 44th question. We have two designs D1 and D2 for a synchronous pipeline processor. Already I told you, in synchronous pipeline processor we have to have equal delays for the stages. So if you have uneven delays, then we have to set the clock to maximum stage delay, right? So D1 has 5 pipeline stages with execution times of 3 nanosecond, 2 4 2 3 3 2 4 2 3. These are the stage delays. So there are 5 stages. Now what is the clock cycle we have to keep for each stage? Because it is synchronous, then clock cycle should be fixed for every stage as same. So that's why I go with 4, right? So it is like having each clock cycle 4 nanosecond, remember. Now we will focus on D1 for some time, because I know that in the question they are asking about the delay of, that means which one is better, and especially they have given that there are 100 instructions. How much time can be saved using design D2 over design D1 for executing 100 instructions? So let me execute 100 instructions. Why I am suddenly changing the flow of the question, I will tell you. Because I know the question, I read the question, you also read the question, you understand. So for D1 pipeline we have to find out how much time they will take to execute 100 instructions. We know that the clock cycle is finally 4 nanosecond, correct? Now how many stages we have in the first pipeline? 5 stages. So what is the formula for executing 100 instructions? Very simple. First instruction takes all the delay. What is the delay? Because there are 5 stages, every stage is going through 4 nanosecond delay, then I can say that 4 plus 4 plus 4, and especially in the question they have not given buffer delay. Otherwise I would have counted that buffer delay also. So it would be 4 4 8 12 16 20. First instruction comes after 20 nanosecond, you know that, right? Now second instruction will come immediately after the next clock cycle, which is nothing but 4 nanoseconds. Now I can say that first instruction takes 20 nanosecond, second instruction onwards takes 4 nanosecond. How many such instructions we have? 99. So 4 nanosecond into 99. This is the total time required to execute 100 instructions. Only first instruction is feeling the total delay, but remaining instructions are taking only one stage delay, which is 4 nanosecond. Now let's generalize the formula. Actually, if you want to have a formula, the formula is like this. In any pipeline model, if you have n instructions, then k stages, let's say, then the time required to execute n instructions is, and the stage delay is, let's say, stage delay, especially maximum stage delay is, let's say, t. Then since there are k stages, first instruction takes k into t delay, correct? Because we should go through all the stages, that's why k into t, right? K into t plus remaining instructions n minus 1. They all take, because so because of the pipelining, next instructions automatically will come for every clock cycle. So every clock cycle means what? Every stage delay, right? Both are same. So every stage delay is t. So that's why each other instruction takes exactly t time. Though now this instruction does not depend on the number of stages. If you have even 5000 stages, doesn't matter. So what matters is the delay of the stage. Obviously when the number of stages are increased, maybe delay will be reduced of each stage, right? So that's a indirect reason, of course. That means, so we don't bother about that. So finally this is a formula for total execution time. Remember, when you have n instructions, k stages, then maximum stage delay is t, then the total execution time for n instructions is k into t. This is the execution delay for one instruction, first instruction especially, k into t, plus remaining n minus 1 instructions will go through only one stage delay, which is t, right? So let us simplify. Let's substitute n value 100 here and k value 5. 5 into t. T is here 4 nanosecond, correct? Maximum delay. 5 into 4 plus n minus 1 is 99. 99 into t. T is nothing but again 4. So it would be, I can say, otherwise we can have a simpler formula if you want. Of course I don't believe in formulas, I believe in concepts. If I take t common, it would be k plus n minus 1, right? So from now onwards, t is the time delay for one stage into total number of stages in the pipeline plus n minus 1, where n minus 1 is number of instructions. Okay, this is exact answer. 5 4s are 20 plus 99 4s are 396. It's, I think, right? It would be 416. Remember, the time taken for this 5-stage pipeline is 416 nanosecond. Let us remember. Now we'll go to the second problem. That means second pipeline. Second pipeline is D2. Let us see the details. That is having 8 stages, k value 8. Okay. Now each with 2 nanosecond execution time. That means stage delay only 2 nanosecond. Fine. How much time can be saved using design D2 over design D1? Yes, we have to find out now total time required to execute 100 instructions over D2. Now we have a formula. What is that? Did you remember? If you don't remember the formula, simple. First instruction takes all the delay, all stage delays. How many stages we have? 8. 8 to the 16 nanosecond. Then remaining instructions 99, and each one will take only one stage delay, which is 2 nanosecond. So that's why I can say that 16 nanosecond plus 198 nanosecond here. It would be 198 plus 6, 204. 204 plus 10, 214 nanosecond. Now the question is what? What is the time saved? How much time you saved if you use D2? 416. Instead of 416, you used only 214. Then how much is saved is 6 minus 4, 2. 1 minus 1, 0. 4 minus 2, 2. 202 nanosecond, right? This much time is saved. We should be careful while solving the problems. So if you do simple mistake in calculations, everything goes waste. That's why be careful. And don't directly, sometimes what happens, you will be tempted and you are not consistent and you are not vigilant and you are not alert. Then what happens? Directly 214 you see and you forget about the question and you tick here. That's why once you solve the question, be calm, relax, and once cross check what he is asking in the exam. Okay, be careful. So that vigilance comes by practice, and that alertness comes by doing mistakes. If you solve lot of problems, you do lot of this kind of silly mistakes, then that will become alarms for you. That means in the exam when you are writing the paper, then whatever the past mistakes you did, they will alert you. If you don't do that, if you don't practice the questions, then what happens? Then all the possible mistakes which a person can do, you will be doing in the exam. That's a danger. That's why I always suggest you to solve lot of numerical problems. Okay. So whoever is attending this lecture now, that is, please remember this thing. You have to solve lot of practice questions. Then only you can avoid the mistakes. Understand? Now we'll see this question which is asked in GATE 2007 paper. In the question they have given that there are only 4 stages. Okay, one is instruction fetch, second one instruction decode, and execution and writing back. Now it doesn't matter for us. Okay, now they have mentioned that multiplication requires 3 cycles, addition and subtraction requires 1 cycle. You remember that. Now we have to execute all these instructions and we have to find out the number of clock cycles required. Let us do that. Only thing is there is a dependencies. There are dependencies. We have to do the operand forwarding. They have mentioned that we have to do operand forwarding. Okay. So if in the question if they don't mention, then you will have 2 options. You can go for operand forwarding and you can solve the problem without operand forwarding. Then the question will become ambiguous. We can't do anything. Then we have to evaluate in 2 ways and we have to see the closest match, right? So what we do is in the question they have mentioned that we have to do operand forwarding. There is no ambiguity. Let us solve this one. What we do is first we focus on the first instruction, addition. Okay. So addition requires fetch, right? Instruction fetch, then decode, then execution, then write back. Okay. So let me use buffers also so that it will be easy for us, right? So write back. So this is a story about the first instruction. Now we have to fetch the second instruction, which is multiplication. Let us fetch here, right? Instruction fetch. Now we have to decode it and we have to fetch the operands. Let us fetch operands here. Okay, is there any problem? No problem. So here we do decoding and operand forwarding. Sorry, operand fetching. Now what is the problem is we are reading the old data because R2 and R3 when you are reading in the third clock cycle, they are old data because after execution you have fresh data here. The correct data of R2 is here. Then we have to do operand forwarding. That's why. So now the question is, what we have to do? Simple. This is the earliest time where you have the result. Simply forward this to this buffer, right? So we have seen it in solving, understanding the theory, right? Now execution, but execution requires 3 clock cycles. It will be like this: execution, 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 right? So this is a normal way of solving the problem. After that, if you see subtraction, then it requires again R6, R5, R4, where you are reading R5 and R4, but anybody is writing R5 or R4? Yes, multiplication. That's why we should be careful. So before completing this multiplication, we can't do it, correct? So be careful. Assume that, let's say, we are fetching the instruction here itself. You can fetch anywhere, not a problem. Now, can you decode here? Yeah, you can decode, not a problem, right? But the problem is we can't execute that instruction. We have to wait, correct? So we will be waiting here. We will be waiting here. Now, since execution result is available and you want it, then the earliest time when we can complete that execution of this third instruction here, execution, right? It requires only 1 unit of time. After that, do writing back. What I want to say is, however, there is here you can't do execution. We will wait. So here you can do execution, correct? Because data is also available. We do operand forwarding. So this operand forwarding is called, here we are doing operand forwarding between execution to execution, end of the execution to start of the execution. This is called operand forwarding between execution to execution. Here also end of the execution to start of the execution, execution to execution forwarding you are doing, right? Then how many clock cycles are required? We'll see. 1, 2, 3, 4, 5, 6, right? So 7, 8, correct? Now, so any problem here? If you decode, no problem, right? So here 1, 2, 3, 4, 5, 6, 7, 8. 8 cycles are required. That's it. In that way you can solve this question. This example, GATE 2015 and set 2 and question number 44. It is little bit ambiguous, okay? Please focus on this question. There are 4 instructions: multiplication, division, addition, subtraction. Fine. And 4 stages: instruction fetch, operand fetch, perform operation, write back. So only 4 stages. That means where are you doing decoding? Here in the first stage itself. And we are doing operand fetch in the second stage, and we are not doing memory operation. Probably you will be doing memory maybe in this write back stage. We don't know, right? That is not mentioned. So finally there are only 4 stages. That is sufficient for us. Now they are saying that we have to do operand forwarding between perform operation stage to operand fetch stage, PO to OF, that is operand forwarding stages. Okay. Now using this information we have to execute these instructions. Now we'll see this question which is asked in GATE 2015 paper and second set 44. So they have, it's not multiple choice question and they have given fill in the blanks. Multiplication R5, R0, R1 and division, addition, subtraction, 4 instructions. We have to find out number of clock cycles required. And there are dependencies. Then we have to go for operand forwarding. They have mentioned that we have to do operand forwarding between perform operation stage to operand fetch stage. Remember that, okay? Only this forwarding is possible. Now they have mentioned that there are 4 stages: instruction fetch and decode 1 stage, operand fetch 2nd stage, performing operation 3rd stage, writing back 4th stage. Okay. Now one more extra thing they have mentioned that, so perform operation is taking variable number of clock cycles. For addition subtraction 1, multiplication 3 and division 5. By keeping these things in mind, we have to solve it. Okay. Simply fill this table. That's it. First instruction is very easy. We fetch here We know that. Then after that, operand fetch, second clock cycle. Then perform operation. Since it is multiplication, it requires how many clock cycles? 3. PO, PO, PO. Then later write back. Done. Now second instruction. So division. It requires 5 perform operations. That means 5 cycles for perform operation. So division R6, R2, R3. Is there any dependency? What are you reading? R2, R3. Are they got updated anywhere? No. Then there is no dependency. Then we can happily fetch normally like this. Fetch, then operand fetch, OF here. Then later perform operation. But already perform operation stage is busy. Then we will have stall cycles, I can say. Correct? After that, here perform operation, perform operation, perform operation. Since it is division, it requires 5 cycles. 1, 2, 3, 4, 5 followed by write back. Done. Now third one, addition of R5, R6. But R5 and R6 are the, I can say, destinations of multiplication operation and division. Then we have to wait for the perform operation of R5 and R6 because they will be only available after perform operation of multiplication, perform operation of division. And of course, the forwarding is possible. That's why we have to wait for PO stage. Let us wait. Just focus on PO stage of this one, instruction number 1 here, right? PO stage will be done here and PO operation will be done here, correct? So we have to start doing operand fetch here, I can say, correct? So that's why you write operand fetch here. Otherwise it is not possible. Then, but we don't know that, right? So we will be initially fetching here, instruction fetch. After that, we have to wait, you see. Don't do operand fetch here because data is not available. So I can say like this, instruction fetch, then wait, right? So after that you do OF. After that, now what we have to do? Perform operation. Here happily we can do perform operation, then write back, correct? Since it is only taking 1 clock cycle for perform operation, everything is good, right? Now, what I want to say is, the fourth instruction, if you see R8, R7, R4, R7, R4 we are reading. Are we updating it anywhere? Yes. R7 is getting updated here. Be careful. Okay. Appropriately we'll plan. So we fetch the instruction here. After that we have to do operand fetch. But one thing, however, we can't do operand fetch. Already I told you, right? So we cannot do operand fetch unless this OF is done, right? So that's why wait. However, we will be doing operand fetch in this clock cycle, correct? Before that you can't do, though you can, if resource is available, we should not do, because between instruction fetch and OF, if you do your OF, then you will be erasing the values of I3 instruction, correct? That's why. So we will be doing OF here, but the only thing is, data is available or not? Data is not available because I3 is doing perform operation here. At the end of the clock, I am assuming that, let's say, end of the clock cycle of PO, data is available. Then we have to wait one more cycle. Then we'll do perform operation here. Then after that, what else? Then we have to do here write back, isn't it? Try to understand. And one more thing. So here IF, OF, 1, 2, 3, 4, 5, 6. See here 1, 2, 3, 4, 5. Here OF. Then here PO, then write back here. Yes, I3. I4's fetch is here. Then 1, 2, 3, 4, 5, 6, 7. We cannot do anything here. I have forgotten. OF is missing actually, correct? That is what actually we have to do here. Then in this stage we will be doing OF, right? Now, to do operand fetch, data is already available. See why I am focusing on OF? Because data should be forwarded between PO to OF. Without data availability, we can't do OF. Understand? That's why. Now let me ask you, whoever attending my lectures, I am asking you this question. Why can't I do OF here? If you do OF here, then this perform operation is still, updating that R7, might be, correct? Then we can't do OF, right? Generally, right? Then we will be stalling. This is the, earliest time where we can do OF. After that, perform operation, then write back. So if this is the case, then answer is what? 15 clock cycles. This is the general answer, like every time. So we'll solve the questions like this, right? Already we solved some questions like this. But in the question exam, in the key paper they have given answer as 13. How can you get 13 as answer, right? So definitely, so to get the answer 13, based on the answer I am updating myself or I am changing my answer. But so we can't, I mean, that's why it is ambiguous question. Let me clearly tell you that it is ambiguous. Why they have given answer 13, then what is there in their mind, I will tell you now. So what is there in their mind to get 13 answer is, while doing perform operation, so maybe they are thinking about the circuit such a way that the perform operation is updating the register file in the first half of the clock cycle. Did you remember in our theory, when we were learning the theory, we did the same thing, right? We were having the clash between write back stage and operand fetch stage. Did you remember? And at that time I said that write back stage is writing the result in the first half and operand fetch is reading the result in the second half of the clock cycle. Then only that is possible, we get the right answers. Here also let me assume like that. Perform operation is modifying or updating the results in the first clock cycle, and operand fetch stage is really reading the operands in the second clock cycle. Okay, second half, first half. If that is the case, then what is going to happen is, we don't really require to wait for this operand fetch to be taken here. We can take operand fetch here itself. My assumption is what this time, because they have given answer 13, I am trying to match that answer. To match that answer 13, then perform operation and OF can be done in same stage, and we assume that in the first half data is available, that will be given to this operand fetch. So in the second half this operand fetch is reading the correct data. Understand? In that way, first half data is updated. Which one this one is I3 instruction, right? Sorry, I2 instruction. And I2 instruction is using R6, it is modifying R6, right? So R6 is getting updated in the 10th clock cycle, first especially in the first half cycle. Operand fetch stage of I3 is reading R6 in the second half of the clock cycle. Then only there will not be any clash and you get the right answer. Let us do that. So finally PO and OF are getting done at the same clock cycle. If that is the case, we will be doing perform operation here, then write back here. Right now let us focus on this time I4 fetch, then wait, because see, between IF and OF or any instruction we should not do anything, right? Go for now OF. Can you do OF here? No, resources problem. Then wait. Then can we do OF here? Yes, I can do OF. Then why? Perform operation is updating the results here and we are taking the result in the second half of the cycle, no problem. So after that perform operation, since it is subtraction only one clock cycle, write back, then answer is 13. So unfortunately, so in the question they are not mentioning all these details, but they are giving the answers as 13, right? So then what to do? What I suggest is, because there are two such questions, okay, so which are following this model, don't worry anything, because whatever we did is it's right. 15 also correct answer, 15 is also correct answer, 13 is also correct answer, only thing is what we are assuming. But if you ask me, sir, finally you tell me which one to be assumed, first one or second one, so that is what ambiguity. Okay, so what you do is, in the exam, in the next paper, if they give this kind of question again, then solve this question with two models, okay, and tally the options, and which one is, I mean, really if there is a 15 answer in options, go for 15. If 15 is not there, if something else is there like 13, go for 13. Understand? So finally I would like to say that this question is ambiguous, and assume that yeah, we can do this problem in two ways.